We are on chapter 1 and 2 for the module 1, okay? So we're going to have a first test on chapter 1 and 2. Most of you have done quizzes and assignment, Moodle quizzes and assignments on chapter 1. Excuse me. And I have checked on McGraw-Hill Connect also. So I can see some of you have been doing some assignment, Connect LS and Connect MH assignments. So everything looking good. If you have any questions, you can send me email and I will try to answer as soon as I can, okay? I'm going to go a little bit of chapter 2 now. I went over, excuse me, chapter 1 a little bit in the last class period. One thing you have to know is, I will go about it. These things. 3 states of matter, classification of substances. Just woke up. Okay, classification of matter into pure substances, mixtures and elements. Then measurement using metric units, mass and volume and length units. And you need to know how to tell the significant figures in a measurement. And measurement has to be shown in scientific notation and normal form. And use conversion factor to convert unit to another. Conversion factor is like 1 inch, 1 foot is 1 inch is 2.5 centimeters, like that. And temperature conversion between Celsius to Fahrenheit, Celsius to Kelvin. There's a slide on the PowerPoint presentation. Okay, that's the chapter 1 slide. So can you hear me?
Yes, sir.
Can you see the slides?
Yes, sir.
Okay, I'm extremely sorry about this. Last Zoom meeting, I was talking to you on the slides, but you couldn't see the slide. I had to go back and refill it. It took a long time, but I want to avoid any mistakes here. Okay, chapter 1 is pretty straightforward. I mean, I will worry more about chapter 2. Let's start doing chapter 2. Because we have a week from now, we have a test close to 25th. Okay, so I want to make sure that you get everything you require. Okay, as I said before, September 25th, we're going to have the first test. So that covers chapter 1 and 2. Chapter 1 is about atom and the periodic table. We're going to talk about elements which are composed of one type of atoms and compounds and mixtures, pure substances, and all the review of chapter 1 again. Then we go into structure of atom and talk about subatomic particles, atomic structure, nucleus, electrons. Nuclei are made up of neutrons and protons. And there are some elements with different masses because they contain different amounts of neutrons. They are called isotopes. For example, carbon-12 and carbon-13. So we want to look at the periodic table in detail. So periodic table is basically the structure of atom. It gives enough information about chemical properties, their reactivity, and electronic configuration, provide the pattern for bonding, ionic bonding, covalent bonding. So electronic configuration is important. And what matters in atomic structure is valence electrons, the outermost electrons. They are the ones that make them react the way they do. For example, alkali metal has one valence electron. They all react with water to various degrees. Reactivity increases going down the group. And we're going to look at the periodic trends. These are the objectives. You have to know element by symbol and be able to classify it as a metal, non-metal based on periodic table. Describe the atom, subatomic particle. Distinguish between isotopes in a certain element. The atomic weight reported on periodic table is average atomic mass based on different compositions of isotopes. You do an average calculation. Now you need to be able to describe the periodic table in terms of groups, periods, S blocks, P blocks, atomic orbital blocks, and different classifications. What are actinides, lanthanide, transition elements, things like that. Now you should be able to write an electronic configuration for an element using the periodic table. Then from the location, for example, certain elements in a group has the same electronic configuration, like halogens have valence shell 7 electrons. And based on valence shell electrons, we are going to draw electron dot structures for atom. So that will be used in the bonding later. Also periodic trends like size and the ionization energy, we are going to look into that. Now, this is a review from chapter 1. Matter is divided into atoms. Matter is made up of atoms and molecules. So that's the atomic view. The chemistry looks into things in terms of atoms and molecules. And all matter is composed of substances and mixtures. Substances are elements and compounds. They have certain set of characteristic physical properties, melting point, boiling point, reactivity, and things like that. even the compound have certain characteristics. Water as melting point, boiling point. Then the mixtures are, on the other hand, different combinations of elements and compounds. Two different elements combine to make a mixture. They are not chemically bound. They are independent. Also, element and a compound and two different compounds like that, they can make mixtures. Mixtures are two kinds. One is homogeneous. That means composition is same throughout. So this piece of alloy metal in the third diagram is a homogeneous. Composition is same throughout. But on the right side, you can see that it's not composition, it's not uniform. That's gold nuggets in a water. So it is heterogeneous mixture. Going into detail, all elements are pure substances that cannot be broken down by chemical reactions. Elements cannot be broken down by a chemical reaction except using nuclear reaction. We are not talking about that here. They are given a two-letter symbol to identify them, atomic symbol. Elements are arranged in the periodic table according to their atomic number, which is the number of protons in the nucleus. Position of the element in the periodic table decide the properties, chemical properties of that element. So diamond here, gold, sulfur. The diamond and sulfur are nonmetals. Diamond is an allotrope of carbon. Carbon has several forms of carbon, graphite, and buckyballs and stuff like that. Gold nuggets here in that rock is a element, metallic element. So we're going back to that diagram again, trying to describe it as molecular level, atomic level, as the way we explain things is mainly not microscopic descriptions of reactions. We are talking about atomic level, like carbon burn in oxygen to form carbon dioxide. That's a atomic, or sometimes it's called particulate view. Compounds are formed by two or more elements combining together. Compounds have formula, element symbol with subscript to show number of atoms. That these ratios are also mole ratio. We're going to talk about that later. Compounds have more than one kind of atom. So this water molecule in the atomic view or molecular or nano view, water is bonded to, in water, oxygen is bonded to two hydrogens, and there are different representations. We use a lot of different representation to show what we are talking about. Water, we don't show glass of water, we show water molecules. Our view is chemist view is only molecular or atomic. So we need to show these structures. There are several ways. This is like on paper, first one. The second one is ball and stick model, space filling model. Different things are used to describe chemistry. Now coming to the atomic structure. Atom is made out of subatomic particles. The particles are protons, neutrons, and electrons. So protons are found in nucleus and neutrons also. Proton has positive charge, neutron has no charge. The mass-wise, neutron is slightly heavier. Mass has slightly greater mass than proton. The reason for that, we think that neutron is formed by the reaction of proton and electron neutralizing proton. So therefore, the electronic charge could be the reason for the extra weight on neutron. Electron has very small mass. The mass of the atom is mainly decided by number of protons and number of neutrons. The sum of the protons and neutrons are called mass number because they are the ones that contribute to the mass of the atom mainly. Nucleus is a very small particle compared to atom. It's like a solar system. Sun is in the middle. There's a huge spans huge space between outer planets and the sun. I mean, this model is not going very far with comparing atom to solar system. But you have to understand nucleus is very small compared to volume of the atom. Now, subatomic particles are kept together by electrostatic forces, mainly. So positive charges repel positive charges. Electrons repel by electrons. Electron attracts by protons. But there's a question, how does neutrons and proton are kept together in the nucleus? That's a whole new ball game. In the nucleus structure, there's exchange forces. They become protons, neutrons. So they're kind of a different area of which is not chemistry. The nucleus is kept stable even though they have a lot of protons. Now in the periodic table, you can get information about subatomic particles. Looking at a box in the periodic table, you can see there's a number on the top, which is atomic number, which is the number of protons in the nucleus. Every atom has the same number of protons. That's the one characteristic of an atom. But if you have same atomic number and different number of neutrons, then that's a criteria for isotopes. Carbon-13, carbon-12, mass number 12 and 13 are two different isotopes with one additional neutron. Different elements have different atomic numbers. C is the atomic number of protons. So we also have another called mass number. Mass number is the number of protons plus number of neutrons. Mass number 35 for chlorine means atomic number of chlorine is 17. There are how many neutrons are there? 35 minus 17. 35 minus 17 is 17. Minus 17 is 18. I'm sorry. Proton number and the electron number is the same. Atomic number. In the neutral atom, number of protons are equal to number of electrons. Now, how do you get the proton number from isotope? You take the mass number and subtract the atomic number, you get the mass number of neutrons. Atomic weight is tricky. Since atoms are composed of isotopes, you have to calculate the average between masses, average masses between these, among these isotopes. Carbon-12 is not exactly 12. There's a little bit of 12.01 because less than 1% is carbon-13. So it goes to higher end of the about 12 atomic weight. Atomic weight in the periodic table are given in AMU, but we mainly use grams per mole. Grams per mole is same as AMU. Grams per mole is useful in stoichiometric calculations. Therefore, the carbon atomic mass 12.01 in grams per mole is used often. Atomic weight of an element. We have example as chlorine. Chlorine has two isotopes. One is chlorine 35 and chlorine 37. They have their exact mass 3497, close to whole number, but their abundances are different. 75% of 35 and 24% of 37. So you multiply abundance by percentage, you get abundances are fraction. Fraction is the one in the last column, last on the right. You multiply 34.97 by the fraction 0.7578 and added to that 36.95 multiplied by 2.422, and that divided by 100. If it is a fraction, you don't divide it by 100. So you get the idea here. Mass of the isotope multiplied by fraction, added them up, you get 35.45. That's the average atomic mass in the periodic table. Periodic table has so many features. They have groups, they have periods and blocks of elements, and you need to know all of them. Most of them are metals. The metal to non-metal line is going between boron, between metalloid elements. So I need to increase the size. The group notation is using numbers 1 through 18, and also there's another notation using 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. The representative elements are 1A, 2A, all the A's except 8A, representative elements. So group 3B to group 3 to group 12 are transition elements. And among the transition elements which are left out at the bottom, lanthanide and actinide series, because to keep the chemical reactivity in the periodic table same for a group, if you stick them there, they will destroy that. We have pulled out 2 rows from the transition metal called following lanthanide is lanthanide. After lanthanide, actinide, after actinide. So there are 2 series. It's called inner transition elements. Transition elements are in the middle, in the main block, where group 3 to group 12. So atomic number is given and atomic mass is given in the bottom of the block, certain blocks. There are other periodic tables which are interesting looking, but they didn't survive. A lot of attempts were made to classify elements according to atomic number. So these never made to the public. So this is like a fashion design. The periodic table that is most useful was kept. Okay. Group 1A is called alkali metal. Group 1A is same as number 1 group. 2A is same as number 2 group. Group B's in the middle are transition elements. But group B also at the bottom is called actinide and lanthanides. The chemistry of transition metal and inner transition metal, lanthanide and actinides, are little different. They show different charges, different variable oxidation state. They are metals nevertheless. They are mainly, these group B elements are rare earths. Most of them are rare. So they are useful in catalysts and a lot of applications. Group 7A or group 17 is called halogens. They are reactive. And group 8A is called noble gases. So this table summarizes where the metals are found and non-metals and metalloids are found. Do you see that metalloids in pink in the middle of going like a step ladder? So that these are called metalloids. If you want to find a metalloid, you look there. You have a periodic table. You can use a periodic table to your questions and answering. Non-metals are on the right side. Metals are on the left side. Metals have certain properties, conduct electricity and solid at room temperature except mercury. Chemical reactivity is different. Non-metals are brittle, dull, non-conducting. Chemical reactivity varies. And metalloids have in-between properties between metals and non-metals. Carbon has 3 forms we call allotropes. Allotropes is a name used for different elemental forms. 3 allotropes for carbon. Diamond has different structure. Graphite has different structure. And graphite is used in pencils. And other one is Buckminster fullerene. So that's discovered some time back. The periodic table also can be shown in terms of atomic orbitals. Now, according to modern atomic theory, we think electrons in atom are found in not like planets around the Earth, around the Sun. They are in orbitals. This is a quantum mechanical, little involved, but you have to know is they are in orbitals, s orbitals. This periodic table shows last electron added to group 1A or group 1 is added to s orbital. S orbital, and you can find which s orbital from the period. Then the B elements, transition elements, last electron added to D, and other elements like 3A to 8A, 13 to 17, 13 to 18 are added to p orbital. And inner transitional actinides and lanthanides and actinides last electrons are added to f orbital. So when you are getting the electronic configuration, you can go through this up to where you element. For example, what is the electronic configuration of lithium? It's 1s, 1s2, there are two places, 2s1. Lithium, sodium. Sodium is 1s2, 2s2, 2p6, 3s1. So number of electrons are same as atomic number. So when you can do the problems sometimes that way. It is shown here how they are filled. But this diagram is not well understood. But one thing you have to show is periodic table. 4s electrons are filled before 3d electrons. On the way that it's going around, 4s are filled before 3d. So there's an exception. It's not the number. The quantum number is 3, quantum number 4. Normally 4 is higher energy than 3, but in the case of 4s and 3d, 4s is filled before 3d. These are the atomic orbitals of different shapes, like s, p, d, f. Now, what is a valence electron? Valence electron are the outermost electrons in an atom. For example, beryllium, electronic configuration is 1s2, 2s2. What are the valence electrons? They are shown in green. Can you guys hear me? Have you lost me or anything? Can you see the slides? Are you guys there?
We can hear you.
Oh, okay, I'm just checking. That's good. The chlorine is 7 electrons in 3sp, 3s2, and 3p5. Those orbitals have the highest quantum number. These numbers in front of orbitals are called quantum numbers. Highest orbital quantum number is the number of valence electrons, like that. Now, one thing we want to show is, even though atom has so much detail, we only show valence electronic configuration. Valence electrons are the important configuration. Valence electron configuration are the one that describe the chemistry of the compound, because the inner orbitals or the co-electrons are not participating in a chemical reaction. Therefore, they don't play any role in chemistry, except helium that has only 2 valence electrons. Most of the atoms have 8 electrons in the valence shell. So if you look at the representative elements here, A's, this is the electronic configuration of the valence shell. So if you look at that, each group has similar valence shell configuration, except 2:3 on the third period. So that shows it is important to know the I got stuck here. I don't know how I got stuck here. Let me figure that out slowly. Okay. I got it. I had to be careful. Okay. Okay. We are here. Let me little bit. Valence electrons are also used to show Lewis dot symbols. Lewis dot symbols. Electron dot symbol, that hydrogen has 1 electron in the valence shell and carbon has 4 electrons, 6 electrons in oxygen, 7. How do you fill them is you fill first around the atom in 4 corners like carbon. Then extra additional ones are paired up like oxygen here. Oxygen had 2 more, then you had to pair up. First you fill in with single electrons, then now the last we're going to talk about is periodic trends. According to the periodic table arrangement, as you go down a group, atomic size increase. Going across, slight decrease in atomic size. The ionization energy, which is important for how strong valence electron is bonded to atom, shows variation in the periodic table. Going across a period, ionization potential increases. It's difficult to remove electron. They become more non-metallic. Going down a group, it's easy to remove electron. Therefore, sodium is less reactive than potassium, rubidium, cesium, francium. As you go down, it's easy to remove. All right. I think this is the last slide on that's the last slide on. I'm going to go through in next class period some review about exam, okay? On 26th we have, 25th we have exam, right? So you guys, I will send an announcement about Zoom meeting on next Friday, next Thursday. You have any questions? Do you have any questions? Are you guys sleeping or are you guys there? All right, I don't hear anybody. Maybe my mic is okay. It's on. All right, I will let you guys go, and if you have any questions, send me email. All right. Okay. Take care. Bye bye.